When people hear the word orbital, they often picture electrons circling the nucleus like tiny planets. That picture is wrong. In quantum mechanics, an atomic orbital is not a path and not a trajectory. It is a wave pattern. More precisely, an orbital is a wave function, usually written psi of r, that describes how an electron is distributed in space around a nucleus. What we usually draw is not the wave function itself, but its square. The quantity psi squared gives the probability density. It tells you where the electron is likely to be found if you repeat a position measurement many times on identical atoms. So an orbital picture is really a three-dimensional probability cloud, not a moving particle on a track. Those familiar orbital drawings with smooth boundaries are also not literal objects. They are boundary surfaces chosen by convention. Typically, the surface encloses about 90 or 95% of the total probability. The electron does not suddenly stop at that boundary. The probability just becomes very small as you move farther out. You may also notice orbitals drawn in two different colors. The colors do not represent positive and negative charge. They indicate the sign or phase of the wave function itself. The probability density has no sign, but the sign of the wave function matters when orbitals overlap, such as in chemical bonding. The reason orbitals have specific shapes comes from the Schrödinger equation. For a hydrogen atom, the equation separates into a radial part and an angular part. The angular part fixes the shape, while the radial part controls how the probability is spread with distance from the nucleus. This structure is summarized by quantum numbers. The principal quantum number, n, sets the overall energy and size. The angular momentum quantum number, L, sets the shape. The magnetic quantum number, m, sets the orientation in space. Together, they define each orbital. A key idea behind orbital shapes is nodes. A node is a place where the wave function is exactly zero. There are angular nodes, which come from the angular part of the wave, and radial nodes, which come from the radial part of the wave. The number and type of nodes determine what the orbital looks like. Start with s orbitals. These have L equals 0, so there are no angular nodes. The probability density is the same in every direction, giving a spherical shape. The 1s orbital has no radial nodes. Higher s orbitals, like 2s or 3s, are still spherical, but contain spherical shells where the probability goes to 0. These are radial nodes. Next are p orbitals with L equals 1. They have one angular node. That node is a plane passing through the nucleus where the wave function changes sign. This creates two lobes on opposite sides of the nucleus, giving the familiar dumbbell shape. There are three p orbitals oriented along the x, y, and z directions. Then come d orbitals with L equals 2. They have two angular nodes. Most appear as four-lobed clover shapes. One of them, usually called dz squared, looks different with two lobes along one axis and a ring around the middle. There are 5 d orbitals in total, corresponding to different orientations. F orbitals follow the same pattern. With L equals 3, they have 3 angular nodes and even more lobes. Their shapes are more complex, and at an introductory level, it is usually enough to know that they continue the same wave-based logic. The size of an orbital is set by scale. For hydrogen, the natural length scale is the Bohr radius. As the principal quantum number increases, orbitals get larger, roughly growing with n squared. Higher energy orbitals are spread out and weakly bound. In atoms with more than one electron, the situation becomes more complicated. The exact wave function involves all electrons at once. In practice, we use approximate one-electron orbitals. These still resemble s, p, d, and f shapes, but their energies and radial distributions shift because electrons repel each other and partially shield the nucleus. Finally, can we actually see orbitals? We cannot photograph a rigid object called an orbital, but experiments can measure electron density and wave patterns that match orbital predictions, including nodal structures. These measurements confirm that orbitals are not just artistic drawings, but real features of quantum wave behavior. The most useful way to think about atomic orbitals is this. They are three-dimensional standing waves around a nucleus. The shapes come from where the wave is large and where it must vanish. What looks like structure is really the geometry of a quantum wave.